Quantum refers to the behavior of matter and energy at an atomic and subatomic level, where the classical laws of physics no longer apply. At this scale, the strange and seemingly random phenomena of quantum mechanics govern the behavior of particles such as electrons, photons, and atoms. In the quantum realm, particles can exist in multiple states simultaneously, known as superposition, and can become entangled in a way that their properties are correlated regardless of distance. Additionally, quantum particles exhibit wave-particle duality, meaning they can display both wave-like and particle-like behavior depending on how they are observed. The uncertainty principle also plays a key role, limiting our ability to precisely know certain properties like position and momentum simultaneously. This fundamental indeterminacy is a hallmark of quantum mechanics, where probabilities replace definite outcomes. Quantum mechanics has been incredibly successful in explaining a wide range of phenomena, from the behavior of atoms and molecules to the properties of solids and liquids. Its principles have also led to the development of revolutionary technologies such as transistors, lasers, and computer chips. In essence, quantum refers to the unique, probabilistic, and often counterintuitive nature of reality at the atomic and subatomic level, where the rules of classical physics no longer apply. Quantum computing is a revolutionary technology that harnesses the power of quantum mechanics to perform calculations exponentially faster than classical computers. At the heart of quantum computing lies the quantum bit or qubit, which is the fundamental unit of quantum information. Unlike classical bits, which can only exist in a state of 0 or 1, qubits can exist in multiple states simultaneously, known as superposition, allowing for parallel processing of vast amounts of data. Quantum computing works by leveraging the unique properties of qubits to perform calculations. Qubits are created using quantum gates, which are the quantum equivalent of logic gates in classical computing. Quantum gates perform operations on qubits, such as adding or entangling them, to manipulate their states. Entanglement is a key feature of quantum computing, where qubits are connected in a way that their properties are correlated, enabling quantum calculations to be performed on multiple qubits simultaneously. Quantum algorithms, specifically designed to take advantage of these quantum properties, are used to solve complex problems. These algorithms are programmed using quantum programming languages such as Q-hash or Qiskit and are executed on quantum processors. Quantum processors are made up of multiple qubits, which are connected using quantum gates to perform calculations. The output of the quantum processor is a probability distribution, which represents the solution to the problem being solved. Quantum computing can be applied to a wide range of fields, including cryptography, optimization, simulation, and machine learning. In cryptography, quantum computing can break many encryption algorithms currently in use, but it can also be used to create unbreakable quantum encryption methods. In optimization, quantum computing can be used to find the optimal solution to complex problems, such as the traveling salesman problem. In simulation, quantum computing can be used to simulate complex systems, such as molecules and chemical reactions. In machine learning, quantum computing can be used to speed up the training of machine learning models. Quantum computers are complex systems that require precision engineering to build. The process begins with designing the quantum processor, which is the brain of the quantum computer. This involves creating a circuit diagram of the quantum gates, which are the quantum equivalent of logic gates in classical computers. The design is then used to fabricate the quantum processor, typically using superconducting materials like niobium or aluminum. The processor is made up of tiny loops of wire that form the quantum bits or qubits, which are the fundamental units of quantum information. Once the processor is fabricated, it's placed inside a cryogenic refrigerator to cool it down to near absolute zero temperatures, necessary for quantum computing. The qubits are then connected to control electronics, which generate the precise microwave pulses needed to manipulate the qubits. These pulses are carefully calibrated to ensure accurate control over the qubits. The quantum processor is then integrated with a classical computer, which runs the control software and provides the interface for programming the quantum computer. The entire system is housed in a shielded room to protect it from external interference. Finally, the quantum computer is tested and validated to ensure it's functioning correctly. This involves running quantum algorithms and benchmarking tests to verify the system's performance. The entire process, from design to testing, requires expertise in materials science, electrical engineering, quantum physics, and software engineering. Keep in mind that this is a simplified overview, and actual quantum computer manufacturing involves many more details and complexities. Classical computers and quantum computers are two distinct types of computing machines that differ in their fundamental approach to processing information. The primary difference lies in the way they represent and manipulate data. Classical computers use bits, which can only exist in a state of 0 or 1, whereas quantum computers use qubits, which can exist in multiple states simultaneously, known as superposition. This property allows quantum computers to process vast amounts of data in parallel, making them exponentially faster than classical computers for certain types of calculations. Classical computers use a sequential processing approach, performing one operation at a time, whereas quantum computers use a parallel processing approach, performing many operations simultaneously. Classical computers store data in a fixed location using memory addresses, whereas quantum computers store data in a quantum state using superposition and entanglement. Classical computers use logical operations and arithmetic operations to process information, whereas quantum computers use quantum gates and quantum algorithms to manipulate qubits and perform calculations. Despite these differences, there are some similarities between classical and quantum computers. Both types of computers require input, processing, and output stages to function. They also share similar goals, such as solving complex problems and simulating real-world systems. Additionally, both classical and quantum computers require sophisticated software and programming languages to operate effectively. They both use algorithms to solve problems, although quantum computers use quantum algorithms that take advantage of quantum properties. However, the similarities end there. Quantum computers have the potential to solve problems that are intractable or require an unfeasible amount of time to solve classically. Quantum computers can also simulate complex quantum systems, leading to breakthroughs in fields like chemistry and materials science. In contrast, classical computers are better suited for tasks like word processing, web browsing, and gaming, which do not require the unique properties of qubits. In terms of architecture, classical computers use a von Neumann architecture with a separate CPU, memory, and input-output devices. Quantum computers, on the other hand, use a variety of architectures, including gate-based, adiabatic, and topological quantum computing. Classical computers are generally easy to program and understand, using languages like C, Java, and Python, whereas quantum computers require specialized expertise in quantum mechanics and linear algebra. In summary, classical computers and quantum computers differ fundamentally in their approach to processing information, with quantum computers offering exponential scaling, parallel processing, and quantum simulation capabilities. While they share some similarities, their differences make them suited for different tasks, with quantum computers poised to revolutionize fields like cryptography, optimization, and materials science. Lastly, quantum computing is a revolutionary technology that harnesses the power of quantum mechanics to perform calculations exponentially faster than classical computers. It works by leveraging the unique properties of qubits to perform calculations using quantum gates and quantum algorithms. Quantum computing has the potential to transform a wide range of fields and solve complex problems that are intractable or require an unfeasible amount of time to solve classically.